Recorded is rolling. It's Wednesday, April 8th. We're going to continue this paper from yesterday. Yesterday, I was showing you guys DC circuits. We're looking at resistors in series and parallel. We started to solve so many circuits. They were starting to get a little bit more complicated, and then the bell was ringing. Okay, so continue there. Now, on the backside is a different perspective of also circuits. You guys see four different circuits that have some models set up. Should give you guys a different perspective, different way to think about these. Okay? And I want to get you guys a lab tomorrow. So I've got these lab paper printed out. Here's what it looks like on one side, and then another side. It shows you how to use a multimeter. Oh, I got a multimeter here. I'll walk you guys through a demo. How do you measure voltage? How do you measure current? Okay, so we'll do all that. And then tomorrow, I want to get you guys either a bunch of 9-volt batteries and a bunch of bulbs. I'll probably do that. Or possibly these cell phone chargers, right? Now the batteries are 9 volts and the cell phone chargers are 5 volts, right? So look at that stuff. One of the other, okay? And then have you guys build some circuits and yeah, so based on today, you should know how to measure all that. Okay. All right, so let's look here. Now, of course, there are different versions of these with different resistance values, right? But you should have all the same geometry circuits. Let's do number 8. Number 8. Okay, we've got a circuit. I'm going to redraw it here. Okay, so draw this box. Okay, and of course, if you guys have paper up for notes, that could be helpful, or just paper in general. You guys, of course, have one of these pages in front of you. Okay, so everybody's circuit on number 8 looks like that. Right, looks like that. Okay. Right, where, guys, what do these two lines represent?
Battery.
Yeah, the battery. That's the battery. Okay, and then what do each of these jaggedy looking symbols represent?
Resistor.
Yeah, a resistor. Right. My classic example of a resistor could be a light bulb. Here's 3 resistors in parallel. Okay. So I'm gonna copy the numbers from this paper. So let's right. Okay, I got 1 ohm right here. I got 7 ohms. Oops, 7 ohms right there. Looks like this one's 3 ohms, and this one's 5 ohms. Okay. Okay. So you have some number of ohms of resistance on each one of those resistors on your paper. Okay. Okay, you guys got your values drawn? Something like this. Okay. Now, yesterday I told you guys there's a process for the more complex looking circuits, okay, which I see some series, some parallel going on here. Okay. So start from the point of view of the battery, and you have to fly over to the complete opposite side of the circuit, which looks like, for my case, a 3 ohm resistor, and then work your way back towards the source, back towards the battery, and find a bunch of equivalent resistances along the way until you find the equivalent resistance for the entire circuit that the battery's pushing us. The battery feels like it's pushing against something, some number of ohms. How many ohms? Right, that's the end goal. Right? So starting from the 3 ohm resistor, right, next I'm going to run to the 7 ohm resistor. Now guys, these two resistors are in what with each other? Series or parallel? Parallel. Now, one way you know it's parallel is because whatever current makes its way to this part of the circuit, the current has to split. And some of the current goes left and some of the current goes right. It gets pushed through both simultaneously, both resistors simultaneously, parallel. Right? So how do I, who remembers from yesterday, how do I find the equivalent resistance of 2 resistors in parallel? What over what? Product over sum. You guys remember product over sum? Okay. That should be like 7 times 3 over 7 plus 3. And then that'd be ohms. Right. Or whatever numbers you have on your paper. Again, everybody has different numbers. Right. But your first step is going to be that parallel equivalence. Right. So for me, I know that's 7 times 3 is 21, 7 plus 3 is 10. Okay. So I could call it 2.1 ohms because 21 over 10, right? Okay. So it's as if these two resistors are acting as a single resistor. That's that many ohms. So now I get to redraw the circuit. So the battery's still here. All right. This resistor is still here. I haven't touched that guy yet. This resistor I haven't touched yet. Okay. But these two collectively act as though it was a single resistor, 2.1 ohms. Okay. So this is an equivalent circuit. Okay. Do you guys also in your notes have an equivalent circuit for your paper?
No.
Okay. Okay. Everybody working?
Oh, I thought you were
okay. Yeah. Just on paper. Okay. So you have blank paper, either your note, ideally your notes, but have paper all over the place too. So you can get some blank paper if you need it. Okay. So this top picture is straight from the page. I just copied that circuit right there. And then I wrote in all these resistors. Now, my resistors are probably different from your resistors because I have a bunch of different versions of these. They're all different numbers. So my numbers look like this. But everybody's first step is to say, recognize that these two on the opposite side of the circuit from the battery are in parallel with each other. So you do product over sum. So product over sum for whatever your numbers are. And my numbers happens to be 2.1 ohms. So if it's a single 2.1 ohm resistor. Right? Okay. Now I have this equivalent circuit. Okay. Now, right. Ooh, guys, think about what the current's doing. The current leaves the battery, goes around the circuit, and then back to the other terminal of the battery. Okay. There's one anode, one cathode. Oh, guys, all three of these are in what with each other? Series. Yeah, they're all in series. Does that mean I can very simply add them up?
Yeah.
Yeah. So the equivalent resistance, I'll say resistance total for the entire circuit, I can just add those three. So I got 5 ohms there. I have 2.1 ohms equivalent resistance. So I'll treat that as 2.1 ohms resistance. Okay, and then I have a 1 ohm guy right here. So it's going to be 5, 6, 7, 8. Let's say 8.1 ohms on my paper. Now, is that a multiple choice answer? It should be a multiple choice answer. Let's see. Do I see 8.1? Yeah, right there. Bing. So I got it. I got it. Okay. How about you guys? Are you guys also getting a multiple? Yeah.
How would we do number 7? Because, or is it just the same thing where you just add them all?
Yeah, we can go back to number 7. No, number 7 is gonna be a process. Okay, you guys ready for number 7? Go back to number 7 then. Number 7. Okay. Okay, so it's gonna look like. Okay, we got this resistor in the middle. We got this guy, this guy. Okay. And I'll do the numbers on my paper again. So I have 1 ohm here. I have 3 ohms here, and I have 5 ohms here. Okay. All right. Okay, you guys ready for number 7? Okay. So you find your battery, which is on the left side. You fly over to the opposite side, which is the right side. And oh, the first two resistors are these two right here. Okay, guys, are these two in series or parallel with each other? Series. Yes, it's series. Because whatever current happens to make its way to this part of the circuit has to go through each resistor sequentially, one after the other. Has all the current has to go through this and then through this. Okay? So, for example, if 5 amps go through this resistor, do all 5 amps also go through this resistor? Yeah, right. It's like amps is kind of like counting traffic. Current in amps is like counting traffic. How many cars? If there are 5 cars go through these stoplights, then all 5 cars also have to go through those stoplights because they're all on the same street. There's only one way to go. Okay? So can I very simply add these together and say 3 plus 1 equals 4? And of course, these are ohms, 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 ohms. Okay. So it's as if there's a single 4 ohm resistor right there, or at least on my circuit. So now I get to redraw the circuit. Okay, I got battery here. I got this many ohms here, which I haven't touched yet. But these two collectively, it's kind of like a single resistor of that many ohms. You guys draw the equivalent circuit on your page? You guys have? Are we good? Okay. Now, again, working our way back towards the voltage source, the battery. Okay. Now these resistors are in what with each other?
Parallel.
Parallel. So the equivalent resistance is, how would you find it? What over what? It's a product over sum?
Yeah.
Yeah. So 5 ohms, 4 ohms, or 5, 4. Okay. So it looks like 20 on 9, whatever that is. Let's see what the calculator says is that. So my paper, it comes out to this many ohms. Do I see that as a multiple choice answer? Yes, I do. That is a multiple choice answer. That many ohms. Okay. Now, while you guys are finishing writing that down, okay, I want to remind you guys too, there's an equivalent math story that goes with this. You guys remember 2 guys painting a fence? Do you guys remember that? Right. What if it takes you 5 hours to paint a fence, and it takes your friend 4 hours to paint a fence? You're going to make a 2-man team. Approximately how long should it take to paint the fence together? 5 hours, 4 hours? Here, the answer's right here. It's about 2.2 hours, right? As long as you're both painting it at the same time, that's working in parallel, right? Because it's parallel math, right? Remember that? Okay. If it takes you and your friend each 4 hours, 4 and 4, well, it'd have to be 2 hours. 5 and 5 would be 2.5. But 5 and 4 comes out to 2.22. Ah, okay. Alright, let's oh, you know what? I did want to show you guys some of these too. Let's see what this looks like. So here's my voltage source, my battery. Right, and I have some Christmas lights here. Alright, let's go see how do I want to make this. Alright. Well, I know that I know how I'm gonna make this. Take something in here. Okay. Okay, tomorrow I'll give you guys these Christmas lights. I have a whole bag of these little Christmas lights that I cut up. Okay. And I'll give you guys probably these 9-volt batteries. Got a whole box of those. I'm gonna bring this up. Okay. So I see one, or no, obviously the resistances are different, so the numbers aren't the same. Okay, but the geometry can be the same. So it looks like one bulb is gonna bridge right across those leads of the battery. So that could look like this. Do you see one bulb just turned on? And the other bulbs aren't on at all yet because I haven't wired them up yet. I got that. Okay. Now, these other two, it looks like, you go back to the original circuit. Okay. You can see the other two in series with each other. But then they each have a lead that's connected to one of the leads of the battery. So I'm going to take these two over here. I've connected them in series with each other. You guys see that? They're in series with each other. And all I have to do is take this lead and connect it to this lead of the battery, and they should turn on. Okay. Guys, but when I do that, are these going to be the same brightness as this really bright one? Are they going to be dimmer? I think they'll be dimmer. Let's see. Yeah. All right, let's get them all on here. Yeah. That's exactly it. Okay. You have one really bright one and two kind of dim ones. Isn't that exactly it? Okay. Because are all 9 volts going across this bright one? Yeah, all 9 volts. But what about the kind of dim ones? Now, there's 9 volts collectively, but how many volts approximately across this one? 4.5. And then 4.5 across this one. 4 and 5, 4, 5, 4, 5 add up to the original 9 volts. Guess what that too? Right. Oh, and you know what? Now it's a perfect opportunity to break out this multimeter. Because tomorrow, when I set you guys up with a lab, you're going to be using this multimeter. Now, there's different version multimeters. If you get an orange one like this, these work the best. Okay. But I need to show you guys. All right, so how about this toggle here? And notice these leads to measure with the multimeter. There are 3 holes for 2 leads. So now what? Okay. You guys see this black lead that's in one says COM? You guys see COM? Go ahead and just leave that in there, all classes. That one you never have to move. But the spread one, it depends what you're measuring. If you're measuring voltage, you guys see this one says volts and ohms and milliamps and blah, 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 right? Do that, right? But if you're measuring current, then pull this out, switch it over to once it says 10 amps for some reason. I don't know, right? So hop in there. Now you can measure the current. Okay. But I'm gonna pull that out and put it back in the volt side to measure volts first. Okay. Now, how you measure with the multimeter? You guys, multimeter. What does multi mean? Does it mean many? Okay. There are many things you can measure. You guys see a toggle going around? You guys see that? Clickety clack. Lots of things you can measure. Now, if you see like a squiggly line, don't do that. That's alternating current. We're going to go for direct current. Anything in the top left here is going to measure volts for direct current, like voltage for direct current. Okay? Now, as I move the toggle, watch what happens to this decimal place. Do you see that decimal just moving around, just sliding around? So it's different orders of magnitude. So I might pick probably that one there. I think we'll be fine. Or maybe even that one. Guess I'm going for like a 9-volt battery, right? 9 volts. Okay. Now, another thing you have to know is how to connect the multimeter. Because again, there's different tools that are all embedded in this one tool. Okay? So for volts, I'll measure that first. You want to connect that in parallel with whatever you're trying to measure because you're measuring really a potential difference. You guys remember that's another name for voltage is potential difference? You guys remember that? Right? Now when we get to the waterfall models, you can think about it being like the top of the waterfall and the bottom of the waterfall. There's some elevation difference. You can think of it that way, right? Voltage is kind of like pressure, isn't it? So like the deeper you dive in the pool, the more the pressure, right? Versus current in amps. Weren't we using a traffic analogy for that? Like a flow rate, like we're counting cars, right? Guys, notice for the current in amps, I'm going to break open the circuit. I'm going to force the current to flow through the multimeter. That wasn't true for volts. That will be true for amps. You see that? Okay. Potential difference in volts, current in amps. There's different ways I have to wire up the multimeter. Guys, everybody pay attention to this? Because tomorrow you guys are going to have to do all of this. You guys are doing all this. Okay? So, and up here, it's only so well you can see with like my thumbs in the way, right? So definitely have this idea in your mind. I think it's one of my posters saying on my wall up here somewhere. Okay. All right, so let's see what this looks like. I'm going to turn this to DC volts. I've got this ready to measure volts. Okay. Guys, what if I put the two? Which one is positive? The red or the black? Which one's positive?
I think
Yeah, the red. Okay, and on the battery it says the small side's positive and the large one is negative. Okay, so I should get a positive value as long as I connect the red to the positive and black to negative. Okay. Should it say 9 volts? Hey, look at that! Guess look at that. 8.8 volts. That's pretty close to 9. 8.8 volts. Yeah, I think that counts. How about what if I wire up these lights like I had exactly like I had them before? This is the same as I had them before. Okay. Okay. And I still go from the did that break apart? There it goes. Okay. Okay, same as before. Okay. Okay. And I put the this lead here and this lead here. Oh, I think I got the lead backwards. I do. You guys see a negative popped up? You guys see that? Okay, got a negative. It should still say well, the number's a little different. Let me switch it back to how it should be actually. This here. Get this here. Alright. Well, it doesn't matter how the lights are wired up. It should read about 9 volts since I'm going lead to lead anyway. I don't know why it's missing a couple of volts there. It's showing like 7. You guys get the idea. It's showing, should show 9. It was just showing 9. Okay, 8.5, whatever. Okay, but how about this? Okay, what if I want to measure the voltage drop across this? Guys, remind me again, how many volts should drop from here to here? 4.5? And then here should be the other 4.5. Let's see if I can wire it up that way. So put this here. Okay. Actually, let me try this together. Okay. Okay. So guys, look what I got here. I made like a triangle shape out of my lights. You guys see a triangle shape out of my lights? But I connect these two leads here. Okay. And then this is the same thing as that circuit. Okay. So the bright one, here's my bright bulb, and here's my 2 dim bulbs over here. Okay. Now I'm going to connect, see this lead right here. And then this black one I'm going to put right here. Let's see how close to 4.5 it is. Oops, not here. Guys, do you guys see 2.9? 2.9? Okay, so, yeah. 2.93, it should ideally be 4.5, but it's kind of, it's in the ballpark, right? Okay. What if I go from here, and I had the leads back. Oh, I had the leads backwards. That throws it off a little bit too sometimes. Okay. I'm gonna put the red one on the positive side. Okay. No, it's still showing 2.7 volts drop from here to here. Okay, so ideally it should be 4.5. It's showing 2.7. I know that's kind of close, right? You see it? Close. Okay. Right, so what could I say for this lab tomorrow? Because tomorrow I'll give you guys a lab paper that looks like this, and I want you guys to draw a circuit and define at every location of the circuit. What are the resistances of the bulbs? What should be approximately the same as each other. What's the voltage drop at each location? What's the current through each bulb, each resistor? And what's the power in watts? So I'll show you guys the example for this one right here because we've been doing this one. So my circuit, I'll draw it vertical like this. Okay. My circuit was looking like this. I have the battery here. I have one bulb spanning across parallel. Okay, and I got these two in series with each other that are parallel with that other bulb. Okay, isn't that what we just did? Okay. And I saw that that the voltage for the entire battery was 8.8 volts. 8.8. So I'll put 8.8 volts right there. Across this guy was also 8.8, and these guys here. I'm going to touch this a little bit just so that the numbers look nice. I'll say 4.4 and 4.4. Let's make believe it said that. It was closer to 3, whatever. Okay. So using this multimeter, I was able to get all the voltage drops. Is that okay? Okay. Okay. So you guys will be able to do that tomorrow, to measure all the voltage drops. Okay. Now to measure the current, I'm going to make a couple of changes. Let's go back and look at this. I'm going to switch from a parallel setup to a series setup. I'm going to break open the circuit, force the current to flow through the multimeter to measure the current in amps. But before I do that, there's something else I have to change. Guys remember these toggle leads right here? I'm going to pull this one out. I'm going to switch it over to here so it says 10 amps. Okay. And then switch this toggle switch to, there's one that works. It's not exactly the orange one. It's right above it. It says so many milliamps. You guys see that? Right. And we're just going to treat this as amps, which I think it might be anyway. So that. Okay. So get my circuit back. Okay. but I have to break open the circuit to make sense of this. Break open the circuit. Okay. So what if I break open the circuit like right here and see how many amps are going to flow? Okay. So I'm just going to lift this side up. Okay. Now I broke open my circuit. You got the triangle setting of lights, okay? But none of them are on. So I'm going to take the red lead and connect it to the positive lead of the battery. Okay. Then take the black lead and attach it to one of these leads, and they should light up again. Yeah, there they go. And I should get a reading. All right, and it's saying 4.2. You guys see 4.2 amps? Or sorry, there's a glare there. 4, well, 4.1, I guess. 4.1. You guys see 4.1 amps now? Is that okay? Now that's through the whole thing. Guys, I just put the ammeter right here. I broke up, open my circuit right here. I got 4.1 amps. So that would be through the battery. Through the battery is 4.1 amps. 4.1 amps. Okay. But then the current splits, and some of the current goes this way, and some of the current goes this way. So I got to figure out how much current is exactly going through this one. So how can I do that? Okay. Okay, so get this set up again. How would I do that? Think about that. Leading into that one. For points. Okay. Let me do it this way instead. Okay. I'm just gonna measure the current going across here. Guys, can I do that instead? Can I measure the current going right here and just kind of add it up and figure it out? Let me do that instead. So I'm gonna break open these right here. On our type. There we go. Break open these. Okay. And I want to measure what's the current going across these two. Now, right now they are not on because they're not part of the circuit yet. Okay. But they will be as soon as I connect the multimeter. So we get this on right here, Okay. Right. And again, you guys see these two leads right here? That's where I broke it open right here. It's the same thing. And so take the leads of the multimeter. Can you guys read the, there's not a glare there, right? Okay. We're going to see how many amps are flowing through that part of the circuit. So connect this here. Oops. I got so many hands. Okay. When you guys have teammates tomorrow, if you have more hands, that makes this easier. Okay. Or if you have a binder clip, so if you have some binder clips, I might break those out. Let's see if I can get this. Yeah, I'm getting a number. It's saying 1.7. 1.6. It's either 1.6 or 1.7. Do you guys see that? You guys see that? Okay. So I'll call it 1.7 amps. Now that's through this part of the circuit, which means it's also through each of these resistors. I have to label these. Let's call them resistor A, resistor B, and resistor C. So A and B, we're each getting 1.7 amps. So I'll call it 1.7. Okay. Guys, all right, you guys ready to do a little math here? We're going to do a little math. If there's 4.1 amps left the battery, and 1.7 amps makes its way over here to this part of the circuit, then how many amps had to go down this street? Can you figure that out? Here, guys, I'll say it again. And you guys, look up here because you have to do this tomorrow. So I have what did I say? 4.1? 4.1 amps left the battery. 4.1 amps. That's like 4.1 cars, you can think of it that way. Or 4.1 gallons per minute. This was like a pie system, right? 1.7 amps to cut down this street. So if I subtract that out, 1.7, that tells me how many amps have to go down this street, which looks like 2.4. Do you see 2.4 amps? So 2.4 amps went down that street. Right? If I measure that, it'd probably get pretty close to that. Okay. Okay. Now, you guys learned a couple of rules over the last couple of days about circuits. I'm thinking of Ohm's law and Joule's law. You guys remember Ohm's law? And then later we'll do Joule's law. Okay. Yeah, guys, what does Ohm's law say? Does anybody remember it exactly? Or if you don't remember it exactly, maybe you remember what variables it talks or related to each other.
If we like almost
Huh?
like
Yeah, something about resistance in ohms, that's part of it. What else?
it's named after that.
Oh, yeah, true, right. Ohm's law. Okay, resistance in ohms is somewhere in there. Okay, it goes like this. I equals V over R, or you can rearrange this and get V equals IR, or I guess you could even rearrange that and solve for R too, right? Okay. Guys, what does I stand for again in this class this week? Yeah, electric current. And that would be in amps, would be the unit. What does V stand for? Voltage. That would be in volts. And then R stands for resistance. And that would be in ohms. Do you see this fraction here, or this line here? It's the same thing. Is that okay? Now, here's what we know from the table. Is let's start with resistor C. Resistor C, I have 8.8 volts going across it, and 2.4 amps going through it. Is there enough information there I could calculate the resistance in ohms? How would you do that in the calculator? Divide, yeah. So I'll take my 8.8 volts, divide by 2.4 amps, and I'm getting the resistance is 3.67 ohm. Maybe I'll just call it 3.7, wherever you want to round it to. So the resistance is 3.67 ohms. Okay. Now, do you think all these Christmas lights are approximately identical? They're all similar number of resistance in ohms? Okay. So I wonder if I'm going to get the same number or pretty similar for these other ones. Let's find out. So here I have 4.4 volts. 4.4 volts is equal to 1.7 amps times some resistance for this resistor, and then the other resistor has the exact same math. Okay? So let's divide that down. That's 4.4 over 1.7. Okay, it's pretty close. Resistance is 2.59 ohms. Guys, 2.59, 3.67, are those in the same ballpark? That's pretty close. Pretty close. So I'm going to do 2.59, 2.59. Or if you just want to call it 2.6, that's okay. Okay. All right, you get that? Yeah. Now, equivalent resistance for the whole circuit. Like, what does this battery feel like it's pushing against? And we did just solve that from this page. Actually, that's what made me wire this up. Actually, this one up in the first place, right? But now we have more realistic numbers because, well, I'm doing it in front of you guys. Okay. We'll come back to Joule's law in a moment. Okay. But I want to figure out the equivalent resistance. So let's figure that out. So I'm going to redraw the circuit. Okay. So I said each of these is about 2.59 ohms, 2.59 ohms, and this one came out a little bit different. It's like 3.67 ohms. Okay. Okay, so let's find the equivalent resistance for this entire circuit. So here's your voltage source. Fly over to the opposite side, work your way back towards the source, and I run into these two. Guys, are these two in series or parallel with each other? Series? Do you guys see series?
Yeah.
Okay. So can I just simply add those together? Okay. What's 2.59? There's two of those. Okay. 5.18. Okay. So it's 5.18 ohms. So now I'm going to redraw the circuit. I got 3.67 ohms here. I got collectively 5.18 ohms right here. Okay. Now, guys, these two, are those in series or parallel? Parallel. So do I have to do product over sum?
Yeah.
So the equivalent resistance is product over sum. So 518 times 367 over 518 plus 367. Okay, I'm looking at this many ohms. Okay. So from the point of view of the battery with this crazy configuration of Christmas lights, the battery feels like it's pushing against a single resistor of 2.15 ohms. Does that make sense? Okay. So I go to my lab page, which you guys are going to have in your hands tomorrow, and I can say 2.15. You guys see this table we're constructing? A lot of the values come from multimeter measurements, and then some of these were coming up with calculations. Right. So it's okay if you do mix and match a little. Okay. Got some measurements, got some calculations. That's okay. Okay. But there's still one column we got to go. And that's the power in watts. The power in watts, you can think of it like the brightness of the bulb. You guys saw different brightnesses. In fact, you guys saw this one was really bright, and these two were kind of dim by comparison. You guys just saw that? Okay. So how can we find the brightness or the power in watts? That's what Joule's law was for. You guys remember Joule's law? So we're going to come back to it. Now's the time. Okay, I gave you guys 3 different perspectives on Joule's law. What was one perspective? Do you guys remember? Power equals, or power equals, or power equals. There were 3 different ways you could get this. What's one way? Yeah, IV, current times voltage. Okay. Now, if that's the only one you know, and you also know Ohm's law, which you're going to use a bunch in this class in the next week, then could you do some substitution and then find the other ways? Okay. Like I know I is V over R, so could I substitute that I with V over R and be V times V over R? That would give me V squared divided by R. Or you could substitute out the V as I times R, and then do I times R. That would be I squared times R. Right. There you go. There's your 3 perspectives on Joule's law. You guys remember that? Okay. So let's run some numbers. I bet no matter how I do it, I should get a similar power for well, any one of these. Okay. Okay. So let's take the top line right here. So I could go power is current times voltage. That could be 1.7 amps times 4.4 volts. Let's see what that comes up to. What's 1.7 by 4.4? I'm looking at 7.48 watts. So 7.48 watts. The next line is exactly the same numbers. So 7.48 watts. Okay, power watts. Okay. Now, I want to check my math. I wonder if I had instead done one of these other formulas, if I would get the same thing. Let's do V squared over R. So that's 4.4 volts squared over 2.59 ohms. What's 4 squared over 259? Hey, it's the same thing. Bing! Or what if I did this version? I squared times R. So I'm looking at the paper, it says 1.7 amps. I'm going to square that and multiply by 2.59 ohms. Okay. What's 1.7 squared times 2.59? 7.48. Hey! Same thing. Bing! Right. Guys, I just ran all 3 perspectives of Joule's law, and they all came out to the exact same number. So you have some choices. You guys get? You have some options tomorrow? Okay. Okay, but I still haven't done this one or the battery yet. So let's do it. So let's do IV here. Let's do 8.8 times 2.4, and I'm going to get 21.1 watts. Okay. Now, guys, 21 compared to 7. Is that pretty close or is that wildly different? That's wildly different. Isn't that like almost a factor of 3? Because that's almost a factor of 3. But I think that makes sense. Because, guys, when I wired this up, wasn't this resistor here really bright? And these two were kind of dim? Yeah, so I think they should be pretty different. Yeah, I can believe that. Now, finally, guys, this last cell. Oh, let me show you guys 2 different perspectives on this last cell. One is I could apply Joule's law at the point of the battery. Guys, could I just do 8.8 times 4.1? Okay, P equals IV. Okay, let's try that. What's 8.8 times 4.1? Okay, so the battery needs to be supplying this times this is 36 watts. You guys, whoops, there you go. You guys see 36.08? I'll just call it 36. 36 watts are being supplied by the battery. Okay, but there's another perspective. Because guys, let's do a supply and demand perspective. Is if the battery is supplying 36 watts, do you think that collectively the 3 resistors are consuming 36 watts? Okay, and I know what they are individually demanding, which are these values right here. So let's add those up instead. With 7.48 plus another 7.48. Oh, whoops, get the glare out there. Okay, so that 7.48 watts plus that 7.48 watts plus what else am I going to type right here? Okay, that many watts plus that many watts plus what? 21.1. Because that's my third bulb. And what should that add up to again? Should be 36. You guys think it's 36?
Yeah.
Oh, yeah. It is 36. Look at that. It's the same thing. You guys see that? See how it's all self-consistent? You see that? Okay. We have about 12 minutes left, so I want to do a couple more things with you guys. Okay. Let's do at least one of these down at the bottom half. Tomorrow will be the lab, and then I want to do one of these waterfall models with you guys if we have time too. Okay. Let's do number, or this one right here. Okay, you guys see this fancy looking one right here? You guys see this one? Okay, let's do that one. So let's, okay, so if you look real close, it's actually number 15 and 16, because I have a follow-up question on this, which is also what's the current going through the battery or supplied by the battery, which we haven't done yet. Okay. And so, guys, in your notes, go ahead and draw the circuit for number 15, 16. looks like this. Batteries here, battery resistor here, resistor here, resistor here. Okay, so guys, that's the geometry for everybody's number 1516. You guys got that? That? Okay, now I'm gonna pick a new paper. So I'm getting some new numbers here. Okay. It looks like this guy is 7 ohms. This guy is 8 ohms. This guy is 3 ohms. This guy is 4 ohms. That's just on the new paper I just happened to pick. Okay. Did you guys also in your notes write the resistances for your circuit on your paper? Which is probably different from mine. Okay. Okay, so let's do the same process that we've been doing. I'm gonna find the battery, which is right here, fly over to the opposite side of the circuit, and then work my way back towards the source and find equivalent resistances along the way. Okay. The next one I run into is this one. So these two resistors, are those in series or parallel? Parallel. You know they're parallel because whatever current makes its way to this part of the circuit has to split and you push through both. So yeah, let's go product over sum. 8 times 3 over 8 plus 3. That's 24 over 11. Looking at 2.18 ohms equivalent resistance. It's as if it's a single resistor. Then redraw the circuit. People have to do this a few times for this one. All right. Haven't touched that guy or that guy. I got this many ohms here, this many ohms here. Okay. But over here, it's as if it's a single resistor. Okay. Now I'm working back towards the source. All right, so keep going, keep going, keep going. All right. Oh, guys, these two, are those in series or parallel? Series. Whatever current goes through this also has to all go through this. There's only a one-way street. So can I just very simply add those together? Yeah. So I'm going to do that. Okay. So do this. Okay, so I've got battery again. I got this guy I haven't even touched yet. But now these, it's as if it's a single resistor of this many ohms, because I can just very simply add them together because they're in series. Okay. So there's my new equivalent resistance, or my new equivalent circuit in it. Do you guys also have in your notes an equivalent circuit for your paper? All right, let's keep going. Okay, so there's one more step for equivalent resistance. Are those two now in series or parallel? How about parallel? So I'm going to do product over sum. Number of ohms. Okay. And you guys are also doing product over sum on your paper and in your notes. So product over sum looks like that. I'm getting this many ohms equivalent resistance. Let me check my paper to make sure that's a multiple choice answer. 8.8. Yes, it is. That's a multiple choice answer. Okay. Now, guys, that's the equivalent resistance of the entire circuit. But for these 6 circuits down here, there's a follow-up question. It says, what's the current total? Like, what's the current supplied by the battery? So I still have to do something else to answer that question. Okay? Guys, if you know the resistance and you know the voltage supplied by the battery, how do you find the resulting current? Whose law? Ohm's law. Which, here's the fraction form. Current is voltage over resistance. Okay. Oh, I forgot to tell you guys, but you might be reading it anyway. 5 volts. Do you see all these batteries are 5 volts? Now, that I did actually make the sense for the same for all the papers. Everybody has a 5-volt battery. Or maybe it's 5-volt cell phone charger. That's like this guy right here is 5 volts. So I'm going to take my 5-volt voltage source. 5-volt potential difference. I'm going to put that on the answer I just got. 3.28 ohms. Or for you guys, it's however many ohms is on your paper. Okay. And that will tell me the current supplied by the battery. 5 divided by 328. Okay. So I'm looking at this many amps. That's the current in amps. Is that a multiple choice answer? Yes, it is. That is a multiple choice answer. Okay. Are you guys also getting how many current in amps on your paper? Yeah, working out. All right. All right, good thing. Okay. Now notice this is the total current. This is supplied by the battery. And so to think ahead a little bit, is once this current, however many amps, leaves the battery and starts going through the circuit, is it going to begin to split and like go different ways down different branches? Yeah. So if I had like 152 cars, maybe some cars go down the straight and some down the straight and some down the straight, but there are always collectively 152 cars, right? that true? Alright, you guys good? Alright, one more thing I want to do with you guys today is let's do one of these waterfall models. Now, all this that you're learning about electricity and circuits, you can actually apply to other fields. Yeah, go right now. Hang on. Right, so all this that you're learning about electricity and circuits, you could apply to actually traffic going around a city or water going through pipes. And here we're going to be treating this battery as a pump and looking at how does the water split and what are the waterfall heights and all that. Okay. Right, so one of these, they have 3 resistors in series. Let's just do this one because this is, I think it's fairly straightforward. Okay. This isn't there just one street. All the cars have to travel on one street, or all the current has to go on one street. Okay. Okay. So if you represented this as like a river, here's the water's pumped up here. So now we've got the water up on this plateau. Okay. Right. Now every time you see one of these resistors, think about that being a waterfall. It's going to be a voltage drop. Right. So the voltage drops. So maybe I pumped up like 9 volts. Looks like I got a 9-volt battery here. Okay. And there's a little voltage drop right here, the splash. And then there's another voltage drop right here, to splash. And then there's a third voltage drop right here, to splash. Right. And then the river current routes back around to the pump. It gets pumped back up 9 volts again, and round it goes. Right? You guys see that? Yeah. Right. And see if you guys are following what I just told you. What does each of these waterfall heights represent again? Okay, yeah, true. There is a resistor there, and the height of the waterfall represents what? Yeah, the voltage drop. There's some voltage drop here, some voltage here, some voltage here. Right. Guys, what did the 3 voltage drops have to add up to? The voltage supplied by the battery. Isn't that Kirchhoff's loop rule? Kirchhoff's loop rule. Right. And so let's see if we can figure this out. Now, I told you each resistance, mine are 2, 3, and 4 ohms individually. Okay. Now, since they're all in series, how do you find the equivalent resistance? Yeah, add them up. Right. Yeah, that's not true for all of these on this page, but it is true for this one. So for me, I think that'd be 9 ohms. Right. Did you guys figure out how many ohms on your page? You guys got that? Okay, how many ohms? Okay. Since I have 2 numbers at the point of the battery, let's go ahead and finish the battery off. Okay. Let's apply Ohm's law here. I have a 9-volt battery pushing against 9 ohms of resistance. Oh, here's Ohm's law. Guys, what is 9 volts divided by 9 ohms? 1? As in 1 amp? 1 amp? Okay. By the way, all the numbers on this page should come out to whole numbers. See how I'm getting whole numbers? Are you guys also getting whole numbers? Nobody should be getting any decimals on the side. Okay. Okay. And then let's go to Joule's law. You guys remember Joule's law? Well, one version is P equals IV, power is current times voltage. Okay, that's one. Okay. I have the current, I have the voltage. Because what's 1 amp times 9 volts? 9 watts. Okay. So does everybody have their entire battery row filled out? You guys got an entire battery? Okay. Row. Okay. Now, look, how could you figure out the rest of this table? Well, guys, let's look at current and amps. Now, there's different ways to fill out the rest of the table, but here's, I think, the fastest way. Is if 1 amp leaves the battery, does 1 amp have to go through that resistor, and also that resistor, and also that resistor?
Yeah.
Yeah, it's like 1 gallon per minute, or 1 car driving around. It's 1 unit. Anyway, is this 1, 1, and 1? Because 1 amp goes through every single resistor. Even though they're different resistances, that doesn't matter. It's still 1 amp. Now that you know the current in the resistance, can you solve for the voltage? Does that sound like Ohm's law, just rearranged? Can I do V equals IR? That's a different version of Ohm's law. V equals IR. Can you guys go I times R and get the V's? So what's 1 times 2? 2. What's 1 times 3? What's 1 times 4? 4. And if I add up all my voltages, 2 volts, 3 volts, 4 volts, does that up to a 9-volt battery? It sure does. So maybe I have like a short waterfall, a medium waterfall, and a tall waterfall. But they have to add up to the elevation of the entire plateau. Yeah. Okay. Finally, power in watts. can I apply Joule's law, the P equals IV, or one of the other versions still, I'll give you the same number. 2 times 1 is 2 watts, 3 times 1 is 3 watts, 4 times 1 is 4 watts. And let's do a final check right here. Because if these individual resistors are demanding 2, 3, and 4 watts, how many total watts are they demanding? Is that 9 watts? Therefore, how many watts should the battery be supplying? 9? Oh, that's what we got before from a different method. So, because whether you apply Joule's law at the point of the battery to get 9 watts, or you add up all the power demanded by the resistors to get 9 watts, it should be the same 9 watts either way, or whatever numbers are in your paper. Right? Again, you should be getting all whole numbers on this side. Right? And that's going to be our pause point today. All right, so tomorrow will be lab day.